Welcome to episode 11 of ExplainerCast. I'm your host, Dave Smith.
And this is Shane Swenson.
And we have some explaining to do. Today we continue our saga on how computers work. Moving on from digital logic, today we're going to go to the next level, the central processing unit.
Yeah, this
sounds like a prison term for some reason.
It does, yeah. It's a very 1950s kind of thing, I guess. So maybe it fits, but yeah, it sounds foreboding.
We will be processed.
That's right.
All right, so last episode we left off with the introduction of how computers combine electrical signals to do simple arithmetic. And we talked about adding numbers together, and we talked about logic where you can say if this signal is on and this other signal is on, then an output signal can also be on, and we can combine those in lots of different ways. And we're going to go really deep on that now. I think we have a lot of material to talk about, which would be really cool.
Yep.
Where to begin?
Yeah, so maybe we should talk about what a computer is and what the basic working model is, because really computers came along before the technology existed to create what we're calling a central processing unit. And their first intent was to really to perform some type of data analysis. And some of the early computers were really mechanical machines that took their input in either a form of a series of switches or maybe some special kind of cardboard cards with holes punched in them. And then they could mechanically take the values that were encoded in that input and perform arithmetic on it, like add numbers together to accumulate a total, maybe find certain statistics from the input numbers. And so these were used for things like the US Census. A company called IBM, International Business Machines, initially made these mechanical tabulators, and then the census was done by putting each household's information onto a punched card, putting all those cards into the machine, and then running all the statistical tabulation on those cards mechanically. And prior to that, there was another type of computer, and that was really a person who was doing the math longhand on paper. They were also called computers.
Yep.
And so here we're really we're talking about electronic computers. So not people, not mechanical.
Not mechanical?
Yep.
Like by which we mean no physically moving parts. Like there are things moving, but
mostly electrons. Yeah.
Yeah, exactly. The electrons are moving through circuits, not physical things touching each other and rubbing and rolling and sliding and things like that.
Exactly. And so some of the earlier computers were built using wire and physical electronic components. And these are the computers that filled a room at a university, say, and used a huge amount of wire, relatively large electronic components, all the way up to devices called vacuum tubes, which essentially looked like small light bulbs and could implement this transistor function we talked about last time, which was based on an electronic input in the form of a voltage, like a high or a low voltage. Essentially, they could turn on or turn off the flow of current between two other terminals on the device. So it was an electronically controlled switch. And we talked last time about how, based on these simple electronic switches and from vacuum tubes, then people developed what were called transistors, which were smaller implementations of that same function, and eventually ones that could be placed on an integrated circuit, which is some type of what we call a chip, like a piece of silicon that has a lot of these little components integrated onto it. And then taking sets of those logic elements like transistors, you can construct the digital logic gates that we talked about last time. So this was the simple one being a NOT gate, which just inverts the input to form the output. So if the input comes in high voltage, or what we might call a 1 in digital logic, it would come back out as low voltage or a 0 in that binary digital logic. And other simple logic gates, like an OR gate that produces a 1 if either of the inputs or both are 1, an AND, which produces a 1 only if both inputs are 1, and then we talked about an exclusive OR, which produces a 1 if only one of the two inputs are 1, but not both. And there are others like what's called a NAND or a NOT AND, which will
Yeah.
produce a 1 or produce a 0 only if both inputs are 1, and so forth.
And then, of course, there's the bananand, which if you put in a 1, you get a banana.
Oh man, I need more of those. Not sure what I do with silicon bananas, but anyway.
They're shocking.
Like all electronics if you don't treat them properly.
Yeah. I appreciate the courtesy laugh, Shane. That was good.
Yeah, you're welcome.
All right.
So let's
continue.
So we've got
please.
very simple logic, and then the question is, well, what can we do with it? And one of the first things you can do is you can say, well, if I have a very specific function that I want to perform, I could just handcraft and design a cascaded set of digital logic gates to do that function. And so we talked last time about adding two binary numbers and how you could build a simple adder with just a few of these simple logic gates. And that's useful if you have a specific problem you're trying to solve.
And if you have a lot of patience, because these things are tiny and very hard to put together, so you would have to be willing to fabricate an integrated circuit, which is itself a very challenging feat.
That's right. Yeah, and when some of these devices like transistors first came out, you could buy small chips that would have these logic gates built into them, and then you could wire them up together on like a logic board. And so you wouldn't have to go all the way to the integrated circuit. But if you want to do this at scale, you are going to want to do it on an integrated circuit. And you can still do that today. There's a type of technology called an ASIC, an application-specific integrated circuit, where you do custom design an integrated circuit, maybe not quite for a single purpose, like you may have some configuration or programmability for it, but again, for a targeted type of function. And what we're looking to talk about today is really a more generalized concept where rather than building application-specific hardware components, we'd like to build something that's very general and generic and then program it in what's called software, which is that the program, in fact, is a specification of what you want the device to do, and then the device uses that specification to execute and produce the results you're looking to produce. And so as computers evolved, then this became part of this architecture, and it's called the CPU, the central processing unit, and it really represents the kind of the core of the brain of the computer. And the goal of it is that it doesn't have to be predefined in terms of what it's going to do. It's available to be programmed or to be given a sequence of instructions, and then it will perform those instructions on the data that's provided.
Exactly.
So CPUs can vary tremendously in the way that they're built, and I guess really there's lots of details, but at a high level, they all have kind of a similar construct. And that construct really comes down to a few basic components. They have some type of logic ability. So they're going to be able to add numbers together, subtract them, compare them, and make decisions based on those comparisons. And this is usually wrapped up in a functional unit called the ALU, the arithmetic logic unit. And it, again, can do specified tasks on data that's available to it. And typically in a CPU, the data that's available in the CPU itself is stored in a set of circuits called registers. And each of these registers can hold essentially a binary number. And so using those logic gates we talked about, you can actually create little bits of memory where you can store either a 1 or a 0, represented again as typically as the voltage being low or high, and a sequence of those together, say initially like 8 of them, maybe 16 or 32 as you go into the 2000s. Now typically those would be 64 of those bits per register. And so the CPU has access to a number of these registers, which each can store the values that they're going to perform those logic computations on. And so as the CPU is executing, it has a control unit, And the control unit goes through what's called the instruction cycle. And the instruction cycle has a few parts. The first part is to read the next instruction from the program that we want to execute. And typically this program is stored in memory that's attached to the CPU. And so we'll fetch that instruction from memory. Next, the CPU will decode the instruction to determine what type of instruction it is. So for example, the instruction might say, I want you to add two numbers together. I want you to subtract two numbers. I want to compare these numbers. I want to set or assign a value to a register, as another example. And the decode process determines what the instruction is and which data it operates on. So in that CPU, there might be multiple registers. And so you wouldn't just say, I'm going to add two numbers together. You would also say which two registers I want to add together and where I want to store the result. After decoding, then it's actually going to execute that instruction, which is typically then going to store the result somewhere in the registers that the CPU has attached to it. And it's going to then update the program counter to go to the next instruction and repeat the process.
And what I find just so fascinating about this is two things. All of this stuff is built using the same transistors and digital logic that we just talked about.
Yep.
But it's this fantastically complicated machine made of these super simple little components. So the idea, you can fetch instructions, put them into a storage. You can then execute an instruction. You can put the result into storage. All of this stuff is done with transistors, including what you just mentioned, the program counter, which is a special kind of register, itself also made of transistors,
yep,
that simply stores the number of the next instruction to run. And that number refers to the program that you gave the computer to run, which is really just a list of instructions, which themselves are just binary numbers.
Yep.
That, we as programmers don't work in binary, but the computer translates the programmer's instructions down to these binary instructions that ultimately get loaded into these registers and then executed by all these transistors. It's actually amazing how complex of a machine that was built from such simple little concepts as, provide electricity so the electricity can flow. It's so amazing.
Yeah, exactly. And the modern CPUs are extraordinarily complex, largely because of how fast they're trying to execute programs. Building a slow CPU that isn't highly optimized is really not a super hard thing to do. It's a relatively small set of instructions that are really required. It's, again, math, comparison, loading and storing values from memory, and a couple other things. And so to me, the beauty of this type of system is that a relatively simple specification of the device, the CPU, and its instruction set enables extremely complex systems to be developed in the software side. And so there is a huge amount of complexity in the hardware really around making it fast, and that's important. But the complexity enabled by computers is also tremendous through this relatively simple abstraction, which is the instruction set architecture, that enables all the software we currently exist with in the world to execute on these devices and produce all the applications and experiences that we have digitally.
It is just incredible when you think about that. Like I was just commenting a minute ago how these little transistors themselves are so simple, but they can be composed into a complex machine. But then you're saying, and I agree, that machine itself is actually pretty simple compared to these software systems that can execute on that machine and create all these experiences that themselves are insanely complex,
yep.
even compared to that simple machine. And like you said, not to discredit, modern CPUs are also insanely complex. So yeah. That is absolutely true.
And of course,
yeah, it's just amazing.
It is. And of course, these modern CPUs are designed and built using computer software for all of the layout, the analysis, the manufacturing. And so we talked a while ago about Moore's Law and this exponential improvement in the capability of integrated circuits over, the last 60 years now. And it's this feedback loop that by starting with very simple computers, then engineers could design all kinds of things, including more sophisticated computers, and then built
Yep.
those most sophisticated computers, which enabled yet another generational step forward. And step by step by step, I think it's just incredible that these have, again, doubled relatively roughly doubled every couple of years, and done so over such a long period of time. In the 1950s and 60s, when this was just getting going, to imagine that in the 2020s we would have these devices that have these massive component counts, they run extremely fast, extremely low power, and we now, building modern software applications, don't even focus on a single computer when we build an application or a single CPU. We design our applications to run across tens, hundreds, thousands, millions of CPUs to do these massively large scale or systems processing, data processing exercises.
Exactly. Yeah, it's amazing. Can we talk a little bit more about each of the components you mentioned here? So you said logic, like the arithmetic logic unit, the ALU.
Yep.
You mentioned registers. You mentioned control unit.
Yep.
And we said all of these are made of transistors, just
Yes.
arranged a little bit differently.
Yes.
And all of them require electricity to be on, or they stop functioning, of course. And even the registers, which are designed to store information, specifically store a number.
Mm-hmm.
And we're not talking about huge numbers here. These are like, somewhere between 16 and 64 bits, meaning 64 ones or zeros.
Yep.
They store these numbers just one at a time, and CPUs don't have a ton of them. Like the early CPUs probably had a handful of registers. Right?
Yeah.
And interestingly, when you turn the power off to these things, they forget the number that they were storing.
That's right. Yeah, it's called dynamic memory, which means you have to keep the power going to it to keep it in place, as opposed to what's called static memory, which you can take the power away and then repower the device later and read back the values. And they're meant to be extremely transient. But yeah,
but very fast. They're fast to store and retrieve information from.
That's right.
For the CPU.
That's right. And there is kind of this general trade-off with an integrated circuit, or really any device, but the integrated circuit really highlights it, which is that the speed of light, the speed of electricity really matter on these devices. So you want them to be small, compact, and have the important things be adjacent to each other. So you literally want that register to be millimeters or less from that ALU so that you can read it, perform the computation, store the new value, and do all of that in less than a nanosecond, less than a billionth of a second. Because
amazing.
Because the CPU is going to execute what we call a clock cycle. At typical CPUs probably clock up to close to 2 gigahertz plus or minus a bit. And so that's 2 billion independent operations per second, which means each operation, in theory, has started and completed in that 2 billionth of a second.
Right, and these operations we're talking about are operations like adding two numbers together, storing information, storing a number into a register, reading a number back from a register, comparing two numbers, 2 billion times a second. Like, can you imagine adding numbers and at a rate of 2 billion additions per second and being able to produce those results correctly every time, 2 billion times a second? I mean, that's what these machines are doing. It's incredible.
Yeah, it really is mind-blowing. And one of the tricks they do play is that this whole instruction cycle, the fetch, decode, execute, and then there's an update stage. Initially, each instruction would go through that cycle independently. So you'd start the cycle for one instruction, go all the way through to storing the result and updating the program counter, and then you would repeat it. And all modern CPUs that are running at high rates are going to perform what's called a pipeline optimization, where they will now have multiple instructions in flight. So they'll be fetching for one instruction while they decode for another instruction, while they're executing yet another instruction and updating for yet another. And they may have even more stages in the pipeline than just those four. They may break them down into substages. And this way, they make each unit of work smaller so that you can run the clock faster. And think of it kind of like an assembly line. It does make the chip more complicated. So for example, if the downstream, like storing the result, would have invalidated a value that was being fetched or decoded or executed that's coming after, then the processor has to go and fix that up and kind of notice and catch that that hazard as it's happening. And so this is part of what's made them a lot more complicated. Is as you go faster, you kind of assume things are going to work out a certain way, but if they don't, you have to undo some work and fix it up.
Yep.
So one other thing we should talk about in this relatively simple model is most software programs don't just start at the beginning and run to the end. You know, they're not just like reading the pages of a book. Do you remember, Dave, did you ever read those Choose Your Own Adventure books?
Oh, yeah, for sure.
Yeah. And so what was the key thing that happened in the Choose Your Own Adventure book? Like, how did you choose your own adventure?
Well, you would come across a page, and at the bottom of the page, it would say, do you want to do X or Y? And it would say, if you want to do X, go to this page. And if you want to do Y, go to another page. And you would continue reading at that page.
Exactly. And so that's essentially what happens in what we call control flow, which is as you're executing the program, you'll come to certain points in the program where there's what's called a branch in the program that says, based on some decision, and usually it's comparing some things, then you have a choice. Either, and the most typical choice is either continue with the next instruction in the sequence or jump to some other location in the code, in the program sequence. And so you could think of that like in that Choose Your Own Adventure, if choice A was just turn the page to the next page in the book, and then choice B was branch and jump to some other page in the book. And that's essentially what happens in the computer code as well. And so that's another important element in the processing cycle, which is to determine what actually is the next instruction that program counter needs to load and execute. And once you have branches, you can now have a program that completes and exits. You can have a program that loops over some input data and performs an operation on all of those elements. So, for example, in that census calculation, you might say, I want to loop over all of the input records and then compute all the totals. And then when I've completed that, I've exhausted the input records, then I exit. And so you can build constructs like that using essentially testing a value to see how it compares to another value like 0. You know, do I still have records remaining or do I have 0 records remaining? And then choose where to go next.
Exactly. And the programmers who design these instructions, especially in the early days before we had more high-level programming languages that make this easier, they literally would have to choose things like, okay, I need a register to keep track of how many census records I have counted so far.
Yep.
You know, and then another register to say how many total census records are there. You know, and then okay, I've got these 2 registers. I know I'm going to use them for that purpose. And then you've got to tell the computer, all right, increase the count of the number of records that I've seen by 1 because I just processed 1.
Yep.
And then I've got a tally of maybe it's like the population count for this area. You know, it's like, well, I'm processing households one at a time. Each household has a number of people that live in it. And so I'm tallying up these people in a third register. You know, and then you've got a statement in your program that says, if the count of households I've processed and the total household count, these 2 registers, if they have an equal number, I want to stop, and then I will output the final register of the total tally of people, right? So just really low-level thinking, you know, to have to figure out where to put these numbers and how to manage your program, what the control flow is. Pretty laborious back then, actually. Much easier now.
Exactly. And so, yeah, if we just kind of talk about some terminology for that, the raw program that the CPU executes, and Dave, you mentioned essentially every instruction to the CPU is a number. It's a binary encoded number, and early CPUs had like an 8-bit number for the instructions, so very limited choices. A modern CPU might have 32 or 64 bits for each instruction, so they can express more information in that instruction.
Which means that there's a bigger number of different types of instructions that the CPU can understand.
Yeah. So maybe more operations you can specify, like different types of operations.
Right.
You might be able to address a larger number of possible registers for the operands to those operations. Mm-hmm. You might be able to have a larger constant value that you're assigning or comparing or manipulating. So yeah, the instructions being bigger can
or be able to just count higher. You know,
Yep.
like I want to be able to count more than 1 billion people. It's like,
Yep.
oh well, this computer can only count to 4 million.
yeah
You know?
yeah like a 32-bit computer might count to 4 billion as an example.
Right. Exactly.
And so those raw instructions just being numbers are really hard for programmers, human beings, to think about and to write down and to process. And so there are some technologies that software engineers use. And the first one was something called assembly language, which was just almost like a very simplistic translation from that machine code, the numeric version of the instruction, to a slightly human readable version.
Yeah, but using letters instead of numbers.
Yeah, basically.
Right.
So you might have a very simple format where you have, say, you name the operation, like add, or maybe mul for multiply, and then you specify which of the registers, and you probably assigned a letter to each register. So you'd say, or maybe a number. You might say add register A to register B, and put the output in register C. That might be one like assembly instruction. And then a piece of software called the assembler takes those assembly instructions and translates them into the machine code, and then that's what's loaded into the computer. And now most programmers today don't even touch assembly code. So instead they write their code in what we call higher level languages. And these are languages like JavaScript, Python, C and C++, and many others. And
countless nowadays.
Yeah.
Probably thousands.
Yeah, realistically. Probably dozens that are meaningfully utilized, and then many, many more that people have either built and abandoned or just performed experiments and projects with. And so then you typically have either a compiler, which reads that code in the high-level language and translates it into assembly or machine code, or you have an interpreter, which reads the code and essentially interprets or executes it as it's reading it. And so it's another example of where we use software to enable, make it easier to write more complex software and do it more reliably.
Exactly. So I want to go back a little bit to the core components of a CPU. And I want to bring in this concept of memory.
Yes.
That we've kind of hinted at, but we haven't dived into it yet. And typically, at least until recently, memory was not actually part of the CPU. It was usually a separate physical component that lived on the circuit board as a neighbor to the CPU. Although nowadays, a lot of chips actually have memory right inside them because Moore's Law keeps delivering smaller and smaller components, so we can cram all that stuff in there, and it's really fast.
Yep.
But setting that aside, we've talked so far about how we can store information. And we've said registers are the way that CPUs do that.
Internally.
But CPUs, yes, internal to the CPU. But CPUs can also store information in a much larger storage area called memory. Or a lot of people will have heard this called RAM, or random access memory.
Yep. And one other, in the early days, this was also called core memory. And so for programmers out there that have had a bug in their program and it resulted in something called a core dump, that was essentially writing out all that core memory so that you could then analyze it and figure out what went wrong.
Cool. I actually didn't know. It's strange. I never thought to ask where the word core dump came from.
Yeah, I think it was
until now.
Yeah, some of the early computers, and they called it core memory. I think of it as like the core of the computer, but they called it core memory because it was magnetic core memory, where you had these fine woven grids of wires that then intersected with little toroidal donut-shaped magnets, and they stored information in those toroidal magnets, and then you could read it back out. And so they were magnetic core memory, thus core.
If I'm not mistaken, I think the Apollo 11 Saturn V rocket had that kind of memory on it.
Yeah, I think that's right. I think I've seen a picture of the construction, the fabrication of the core memory for some of those early space program systems. It's incredible to see how we sent people to space and like hand building computers and memory to do it.
I know, it's amazing. So memory, it turns out that most useful software needs to be able to store more information than just call it a dozen numbers in registers.
Yeah.
Like for example, think about the census example. We need to store the names of people. We need to store street addresses.
Yep.
We need to store birth dates. And when you start thinking about even one household, you quickly exhaust the amount of information that can be stored in, say, 12 integers.
Exactly.
In a register. And I picked the number 12 at random, but that's not too far off from what early CPUs would have had in terms of number of registers.
Right.
So we need a lot more than that. We need hundreds of numbers, maybe thousands. And actually, modern computers have billions and billions of numbers that they can store in memory outside of the core CPU itself. There's the word core again.
Yep.
So how does this work? Well, now imagine that you have a whole pile of transistors whose only job is to have like an input that is an address, a number, and an output that is also a number that tells you what number is stored at the address number that you were given. And that's this whole thing's job, is you give it a number, you can say store it at this address, or you can give it an instruction that says, I need to retrieve the number that is stored at this other address. And memory does that.
Yep.
And it allows the CPU in a much, much slower way. And like when Shane was saying that modern CPUs can run at billions of operations per second, typically memory cannot fetch and retrieve information at that same speed.
Yeah.
But it's still useful. Even though it's slow, it's useful for longer term storage of information.
Exactly. Yeah, and the assumption in this computer architecture was that there would be some type of storage external to the processing unit. And again, it's a size cost constraint where if you could put all this memory into the CPU, you would, but it's just not physically practical to do it. So
at least it didn't used to be.
That's true. Yeah, more and more you can do that, and now there's a term called like a system on a chip, where you kind of put all the components of a computer into one chip, and you can make it now quite small and compact. And
yeah, and it's actually amazing because that memory that's actually stored in the system on a chip, so proximate to the CPU itself, is a lot faster than the memory that has to go on physical traces of little metal traces that are on a motherboard that could be inches away from the CPU.
Yeah.
And I'll just, at the risk of saying something wrong here, I'll say that Apple has probably delivered more of these integrated system on a chip systems with memory and CPU all in one chip. They've probably delivered more of those than anyone in recent history because they kind of popularized this idea in consumer grade electronics. And now almost all the computers you buy from Apple are like this. They've got the memory and the CPU all in one tiny little chip that's smaller than a postage stamp.
Yeah, and I haven't looked, but I would assume mobile devices, like mobile phones and so forth, will do this too.
I would assume so. I would assume so as well.
But when you talk about it being slower, I mean, it's true. There's a trade-off for size, and now that size is typically measured in gigabytes, and I guess more terminology. So 8 bits together are typically called a byte, B-Y-T-E, and it's thought maybe that's a portmanteau of by 8, because early computer designers built their memory in blocks of 8 bits at a time, called a byte. And
no way. Is that true?
I think it might be. I wasn't there, but
that's
the story I've heard.
That's incredible. I have not heard that before.
Yeah.
Got it. By 8. I love it.
Now, they did play with the pun quite a bit. 4 bits was a nibble, N-Y-B-B-L-E.
Right.
And like 16 or 32 bits was a chomp. Like,
yes.
You never hear those terms anymore, but anyway.
No, you just hear about bytes now.
Yeah. And then when we say giga, we're using I guess like the metric unit prefix, where giga means billion. So a gigabytes is a billion bytes, which is 8 billion bits. And I mean, a modern mobile device, mobile phone, or a modern computer is going to have somewhere between 4 and 64 gigabytes of random access memory. So huge numbers compared to what you could probably fit onto most CPUs. I mean, that's more than there were components on a CPU for much of the history of CPUs.
Yes,
and
it is amazing.
And when we talk about the CPU being clocked in the gigahertz range, a couple gigahertz, typically, I think off-chip RAM, random access memory, would be clocked in the low hundreds of megahertz. So probably in the 100 something to 200 something megahertz or million cycles per second range. So
Meaning you could read or write a couple 100 million numbers per second out of the memory.
right, right. Compared to the CPU wanting to process a couple billion operations per second. So you got a factor of 10 difference in the clock rate. And then there is the latency itself, just how long it takes to transfer that information as well. And so the result is that the CPU is very fast when it's working with information that's in registers, and it's still fast, but an order of magnitude slower when it has to fetch and store information to and from that, the RAM, the remote memory, especially if it's happening on every cycle.
Mm-hmm. Which it just can't, right? Like the memory can't keep up with that.
That's right. Yeah. So,
but that worked out pretty well, because it turns out a lot, not always, but a lot of computer programs, they would need to do multiple calculations on the CPU before they would need to put a result back into the memory.
Yep. That's the first thing. Yeah, you might do multiple steps. The next one is you might perform multiple operations on the same pieces of data. So you might want to write them back, but you might immediately want to read it again. And so there's a mechanism called caching, where the CPU will have some amount of memory that isn't the primary source of truth for this information, but it stores a recent copy. And there's a whole system to make sure that the cache value is still correct and still valid. But if it is, then you have what's called a cache hit, and you can load that value from the cache back into a register very quickly, continue processing, and then write it back out when you're done. And so this is based on a concept called locality of reference, which is that often computer programs work on the same data for a while, and then they move on to a different set of data over time. And so
that's in a different location, specifically.
That's right. Yeah, different location in memory or something. And so the result is that this caching concept can dramatically reduce the number of round trips you have to make to the main memory system and keep that CPU operating at full speed.
And there's one very important piece of memory that the CPU needs quick access to all the time, and that is the program itself.
Of course.
And I believe that one of the main reasons that caches like this were first created, and the earliest exposure I have to this was in the 90s when you would buy CPUs. One of the specifications was how many kilobytes of L1 cache does it have? How many kilobytes of L2 cache did it have? And the more cache that a CPU had on it really meant that your programs would run faster, because the CPU could load memory up front into the cache, and then it could execute quicker on instructions or data. And so you got a big speed up if you bought one that had, more than 128 kilobytes of cache, or it's got 256 kilobytes.
Exactly.
But importantly, that's how the CPU loads its program, which again is just a list of numbers that need to be executed, into a location where it can actually pull the next instruction fast enough to be able to keep running at its full speed. Which, if it was pulling every instruction from memory, one instruction at a time, it would never be able to go over 100 or 200 megahertz.
Yeah.
Assuming that's the constraint on the memory. But since it loads batches of instructions, maybe hundreds or thousands of instructions, into a cache that, again, is probably just a set of things that look a lot like registers, but in a big block on the CPU itself, now it can source information, or the numbers from those cache locations directly at full speed into the computer, so that it doesn't have to wait for the memory every time it needs to figure out what the next instruction is to run.
Yep, exactly. Yeah, because you don't want to be waiting. The CPU will do what's called stall if it has to wait for either program or data to show up. And so keeping it full all the time is super important. And you mentioned L1 and L2, and this again is just more layers of hierarchy. So think of the registers kind of like L0, like they're right there for the CPU.
Yeah.
And then usually those chips would have a small amount of L1, level 1 cache, which is very expensive per bit, but very fast. And then a larger quantity of level 2 cache, which essentially if the level 1 cache was full, then you would flush some of that cache down to level 2 in case you need it in the near future, a little bit cheaper, a little bit slower, but you could, as a result, put more of it on the chip. And then if something expired in the level 2 cache, then you would flush it back all the way out to main memory. And so the goal would be that you have enough locality of reference that your program and data are in cache, and something that's also called as the working set, which is how much data and program are you actually iterating over in these loops. And if all that's in cache, you're running at full speed. The more of that that's in main memory, then you'll see the CPU performance dramatically diminish as you're doing all that fetching and waiting.
Yeah. And you mentioned that these CPUs, if they don't have anything to do, that it's called a stall. And it's interesting because CPUs are never doing nothing. And that's because they are powered by a clock signal that is oscillating at a fixed or variable frequency, but still oscillating all the time. They don't just stop.
Yep.
And so if you aren't giving them something to do, they're going to literally twiddle their metaphorical thumbs.
Yeah.
And I'd like to just check my knowledge on this one, Shane, but I believe that most CPU architectures have an instruction called the no-op or NOP that they execute when there's nothing else to do.
That's right. And essentially it means do nothing except increment the program counter. And so you can put that in a sequence if you just want to fill some space in your program's listing of instructions, or you can essentially do a series of loops. And so typically a CPU, when it's waiting for something, now there's a few different reasons it would wait. If it's waiting for data or program to become available, then it will stall and it will kind of pause while it waits. What you're probably referring to is it's waiting for the program it's executing is actually waiting for something to happen. Maybe it's waiting for someone to enter something, some input, or it's waiting for some external signal. And so typically then the CPU will be in a tight loop, and it maybe will wait a little bit for each cycle, but it'll just go to check and say, is the thing I'm waiting for available yet? Which might take the form of, has a particular register value that represents an input connection changed from a 0 to a 1 that tells me data's available, and now I can go process it, or something like that.
Mm-hmm.
And modern CPUs do have other optimizations like variable clock rate. So to save power, if they're not being fully utilized, they'll slow down the clock. If they're, and there might be parts of the CPU itself or the overall chip, when they're not needed, those parts will actually shut down and they won't be activated until they're needed. And that again just reduces the total power draw being utilized by the processor. And this has really been driven by mobile devices, because the bane of the existence of a mobile device is a dead battery. And so a CPU that is really efficient and only uses energy when it has something important to do can then extend that battery life and give a much better experience.
Yep. I still remember my first variable frequency CPU. I think it was in the year 2000, and it had so-called Intel speed step technology.
Nice.
And I was always turning it off because I'm like, no, I want my laptop to be fast.
So I could think back, I can't remember exactly when this was, but I had a computer or two, desktop computers, this would have been in the 90s, that had a turbo button.
Oh, yes.
And so if you had the turbo button on, it was faster. And if you had the turbo button off, it was slower. And the use case that I had for turning the turbo button off was if a game was programmed in a way where it just used sort of throwaway instructions as a way of setting the pacing of the game, turning the turbo button off might literally slow the game down. You know, think like Tetris or something like that. Like Tetris with the turbo button on was way harder than Tetris with the turbo button off, because it literally would go faster and slower.
In other words, the software made an assumption about the clock speed of the CPU that it was running on.
Yes.
And used that to time the game.
Yep.
And so these computer vendors, when they came up with faster CPUs, realized, oh no, these games won't play right. So we're going to have to give users the option to slow down their CPUs.
Yeah, exactly. Yeah, these days you would use a timer system that the CPU provides, and you just check the clock. But yeah, back then you would just say, I'm just going to loop for 100 cycles, and 100 cycles of no ops, and then a second will have passed or whatever, and I'll go do the next thing, and a thousandth of a second or something will have passed. But
And thus continues the time-honored tradition of software developers not being willing or able to change their software and hardware vendors having to change to accommodate it.
Yeah, that's right. I think all platform providers
Exactly.
Yeah, all platform providers probably suffer from that. I mean, I can think of well, poor Microsoft and all the compatibility mode down to the very bugs they had to preserve because certain programs stopped working when they fixed the bugs.
Mm-hmm. Programs that depended on bugs. Amazing.
Seriously.
So I would like to take, we've probably just got a few minutes left, and I would like to talk about how you get a computer to start.
Okay.
Because we've talked about memory that contains your program, but we haven't talked about how the program gets into memory.
Yep.
We've talked about the CPU that can execute instructions, but we haven't really talked about how it gets those instructions.
Yep.
And when you think about a machine that's capable of doing all this stuff, but it's not turned on, and then you turn it on, what's it going to do?
Yeah.
And the answer is, by default, nothing. Like there's nothing for it to do.
Right.
So you have to give it these programs to execute. And again, these programs are just a sequence of numbers.
Yep.
And each number itself represents an instruction that can be run, and each instruction sits at a location in the program. So how the heck do we go from a dark machine that's doing nothing to now a powered machine that's running a program I want it to run?
Yeah, exactly. And there is what is sometimes called a bit of a bootstrap process here, which refers to this idea, this metaphor of pulling yourself up by your bootstraps. And the idea is start with something really simple and then initiate enough kind of context that you can do something a little more complex, and you kind of work your way up step by step. So I haven't checked this carefully myself. Dave, do you have this in mind? I can tell you what I think it is, but I'm actually curious if you're asking or if you're telling here.
I only have conceptual understanding of this. I couldn't talk too specific, but maybe we can muddle our way through it together.
Sounds good. So a couple terms that I remember seeing in, I don't know, now when I boot my computer, it's just a black screen until it shows up with the login prompt. But older computers didn't used to do that. They used to tell you more what they're doing on the way. And so there's a couple things that contributed that you'd see. One of them, when the computer first started up, is you would see a power on self-test. It was post, P-O-S-T.
Yep.
And it's just kind of running through, can the CPU sort of communicate with itself and with the components attached to it? And one of those components attached to it was something called the BIOS, the basic input-output system. And the idea with the BIOS was it was a very simple program, very low level, we would call it, that would enable the CPU to interact with the other components on the computer itself. Like,
and Shane, before we go too far, where was that BIOS program stored?
So that was stored on a chip, like essentially on a static memory chip. So it was kind of what we would call kind of burned in or stored in a way that was not as easy to change on a small chip sometimes called your CMOS chip.
That either didn't require electricity or required very, very little in the form of a little battery that would hold it there.
That's right. Yep. And sometimes there were another type of programmable device where you could put like the chip into a special programmer and it would use fairly powerful, I don't know if it was magnetic field or electric current, to go and set some logic states, and then you could later read those values back out using a read process, and they were very stable. And so they were like a programmable read-only memory. So we talked about random access memory in your modern computer called RAM. And the random access meant two things. One is it meant you could use those addresses to read whichever values you wanted, but it also was modifiable. You could read it, you could write it. And ROM, read-only memory, you program it separately, and then from that point forward, you just really read it. And so you'd have some type of ROM that would have a very simple program to just get things going. And essentially, you need to put the CPU in communication with the memory so that it can start to, and also with your other storage devices. So typically, you would have some type of either fixed disk, like what we would call a hard drive or or now an SSD, solid state storage device, or you had back then removable disks, typically called floppy disks, because the magnetic medium inside them was flexible, like made of mylar plastic. And so when that CPU boots up, it first does this power on self-test. It then begins to execute this basic input-output system BIOS program so that it can find out what actual program you want it to load and execute. And that means it needs to communicate with the memory, and it needs to communicate with its storage, its external storage in terms of the media that's holding the program you want to execute.
Right, and that's a topic we will get to at a future episode. But suffice it to say that this BIOS allows the CPU to access the initial program that needs to run, followed by the user program, or usually an operating system,
right?
Which we'll definitely talk about that later as well.
Yep.
To get this whole process going.
Yep.
From no electricity flowing to, okay, I am ready now to execute your instructions, whatever they are.
Yeah, and yeah, there's probably two just quick abstractions to talk about there. So today we've been talking about the CPU, which is a general purpose instruction processor. You give it a set of instructions and data, and it'll do what you tell it to do in those instructions. And then these get deployed really into a couple of contexts. In one context, you have one program you want this to run over and over again. So think about like a computer chip that you're putting into maybe an embedded device, like on that, on a rocket that's going to the moon, or in a printer or something like that. And so you might even have read-only memory that has the program you want it to run. And it's going to start up, power on, and it's just going to run that program. And the other way that we typically set things up is we actually want the computer to run general purpose on-demand programs. So then after this initial startup sequence, we'll actually start executing what's called an operating system, which provides an environment to load and run programs that are brought to the computer or asked for by the user later. And so it's really even another layer of indirection that now you can run programs on demand instead of just by having previously specified it. And yes, be interested to talk about that another time.
Yeah, so fascinating. It really is amazing how hard it is to get a computer started. Like, it takes a ton of work, ton of code just to get the darn thing going. It's not like a typical machine, oh, here's my hammer, I'll just swing it. Like, oh no, this hammer has a boot up process. It needs to test itself. It needs to verify all the memory is good. It needs connection to the storage. It needs connection. Anyway, it's just crazy.
Yep. And it all happens quickly, and it's really just because of decades and decades of engineering that it happens to look as easy and be as reliable as it actually is. Because you're right, there's a tremendous amount of complexity contained in those processes.
All right, have we covered enough material for today, Shane?
I think so. I think this was cool. And yeah, it really sets the stage for going deeper into computers and software and systems. But yeah, I think this was a good one.
All right, thanks a lot, Shane. We will catch you next time on ExplainerCast.
All right, see you later, Dave.